Yeah, today I'm going to talk about this integrability in one-dimensional classical non-equilibrium statistical mechanical models. So this program, for this program, there are many people from various fields, and I'm from statistical mechanical side, and I have been in particular working on non-equilibrium statistical mechanical models. So today I would like to talk about the integrability of such systems, and and this time I will talk about some particular aspect of the appearance of classical integrability in the description of so-called large deviations in statistical mechanics, non-equilibrium statistical mechanical models. And my talk today will be based on a collaboration with Kiron Malik from Sakurai and Hiroki Moriya, who is my PhD student in Tokyo. Okay, so there's already a reference for the talk today, and so this is it. So if you have some interest, please take a look. Okay, so this is very quite a general introduction to the subject itself. These are non-equilibrium statistical mechanical problems for classical systems. Yeah, now maybe so this is really all the way of thinking, but let me start from this. So, of course, from the time of foundation of equilibrium statistical mechanics by Boltzmann and Gibbs, people got interested in establishing non-equilibrium statistical physics, right? And then the natural way to think is to consider some dynamics, maybe Hamiltonian dynamics for classical systems, which maybe tend to go to equilibrium situation. So then we have to study dynamics of particles and so on, right? For equilibrium system, we can use maybe Gibbs ensemble. So even though we use the same Hamiltonian, we don't have to solve the dynamics. But when we are interested in non-equilibrium situation, we basically have to try to solve the dynamics described by Hamiltonian equations or Schrödinger equation. But this is quite difficult, simply difficult, right? Due to the existence of chaos and so on, of many particle systems, it's practically impossible to solve the dynamics. So then we have to think about a little bit different way. Of course, now I think people are more interested in quantum dynamics, as in the people in the other program at this KITP. And last week we attended, there was a lecture about the recent developments about understanding quantum dynamics, and there are many developments which is also a bit related to this kind of thing. But today I'm sticking to a very classical way of looking at things. And one very famous and important example of this constellation in this direction was the so-called Fermi parallelogram chain. So this is maybe n particle system connected by strings with the potential given this way. When alpha and betas are 0, so this is just a harmonic potential. So then, of course, the dynamics of these n particles are very simple. This can be solved by Fourier analysis, and the kind of general motion of the system is just a linear transpose of the so-called what is that? The normal modes, right? So this is just a simple linear problem. But and for this linear problem, there's no thermalization, so they are just oscillating, right? So these people, so they got interested in how thermalization may occur for classical systems, and they thought that maybe if one introduces nonlinearity to the potential, such system may go to thermal equilibrium just as a course of time, right? And of course, it's not possible to solve this problem, but at the time, so this Fermi is the famous Fermi, so he was involved in Manhattan project. So he had access to the current of the art computer at the time in the 50s. So he took up this problem and tried to see what happens for nonlinear particle systems, right? And then at the beginning, they observed some tendency for thermalization. So they started from particular mode of the harmonic, linear system, then they observed a kind of redistribution of energy to other modes, right? But when they waited a little more, they saw almost recurrent behavior to initial condition. And this was the kind of conclusion at the time, because this was just a kind of numerical simulation, and it was just impossible to really solve and what's happening for long time behaviors. But anyway, so this paper was just a report at the Los Alamos. This created a new interest in non-equilibrium problems for nonlinear systems, right? And so this system is still attracting a lot of attention in non-equilibrium statistical mechanical community. So this shows anomalous transport and so on. Okay, anyway, so this is difficult. So instead, one rather simple idea to consider non-equilibrium problems still for, with nonlinear interaction is to replace this Hamiltonian dynamics by stochastic dynamics. And in particular, it is useful, and it is already pretty practically useful to take Markov dynamics, which means that a state of a system just evolves by kind of some rule, which just depends on the state at the time, right? So there's no dependence on the whole history. So this is just a pictorial way of writing this time evolution equation for mass equation. So probability may be thought of as a kind of vector representing probability at each state. So then this first derivative of P is simply given by LP. So this is again vector, and L is a matrix, which is sometimes called transition rate matrix. So describing transition from state I to state J in a infinitesimal time dt, right? So then now, instead of studying Hamiltonian dynamics, we may consider Markov dynamics, which does not have a problem of serious chaos. So already this has an advantage, right? Okay. And there are many works in that direction. But here, for us here, we are particularly interested in some particular specific Markov dynamics, which is integrable, right? And so there are many models, but today I talk about one of the most well-known and standard models in non-equilibrium classical statistical mechanics, which is ACID. So this is an abbreviation, asymmetric simple exclusion process. So there are various versions, but today I stick to one-dimensional version, in which we have one-dimensional lattice on Z, and there is a particle that is empty at each side, and each particle tries to do asymmetric random walk with rate P to the right and with rate Q to the left. But so there are exclusion interactions among particles. So if there are two particles on neighboring sites, left particle cannot hook to the right particle cannot hook to the left. That's it, right? So this is ACID. Yeah. So is the model clear? Yeah. Okay. So yeah. And yeah, so this is standard model, and yeah, even though this is quite simple, so this still already contains some nonlinear effects coming from this exclusion interaction, and yeah, this shows far from equilibrium behaviors. So yeah, so this is kind of standard model, and yeah, maybe you may think of this as a kind of particular limiting case of some kinetic version of Ising model at infinite temperature. So now there's already no influence from interaction, so there's only volume exclusion effect, right? Okay, and as a non-equilibrium problem, one of the most important quantity is the current. So for equilibrium system, there's no current, but for non-equilibrium system, usually there's some current, right? So we're interested in average or fluctuations or distributions of this quantity current. Okay, and so there are maybe two particular cases of this general ASIM. One is the so-called tacit, totally asymmetric simple exclusion process, in which particles hop only in one direction. Even though the model becomes quite simpler, this captures basically the same universal behavior as for general ASIP. And so from technical point of view, this is much simpler. So there are many works on tacit. But today, in fact, we focus on the case of symmetric case in which we take P equal Q, so that each particle tries to do symmetric random walk, not asymmetric, but with exclusion interactions, right? And if the density is uniform, there's no current, and the hydrodynamic description of a set is simply diffusions. In that sense, the set is considered to be a bit too simple. But if we consider distribution of current and so on, this symmetric case already contains various non-trivial behaviors, and today we will focus on that. But at this point, I'm talking about the general asymmetric case, ASIP. And for you, so you may wonder, how this is integrable, but there's one simple way to look at this. In fact, this transition weight matrix, so a generator of this Markov process, is a kind of matrix, big size matrix, right? For this, for the case of ASIP, when we consider system with system size L, so this matrix L is just 2 to the power L times 2 to the power L matrix. So this is a bit similar to spin chain, right? And indeed, at least for the case with particular boundary conditions, so there is a simple similarity transformation which connects the generator, Markov generator of ASIP to the Hamiltonian of XXC spin chain. So then it is kind of obvious that, of course, XXC is a quantum integrable. So in that sense, ASIP is also integrable, right? And so in that sense, these kind of models may be called integrable stochastic processes. But the structure of the integrability for this model is basically quantum integrability, not classical integrability. But somehow, so by this connection, one can apply, for example, standard techniques of quantum integrable systems like the Bethe ansatz and so on. Yes?
How XXX enter the D? To be question, can you repeat again as?
So L is for the ASIP is kind of 2 to the power L times 2 to the power L matrix, which has the kind of same size as the Hamiltonian for XXC. And indeed, there's a similarity transformation which connects them. Yeah.
The Hamiltonian.
Yeah.
And the size is.
So of course, for Markov process, so this L does not have to be Hermitian, right? So this should satisfy some stochastic condition. So in that sense, they're kind of fundamentally different. But from that more technical point of view, as a just matrix, then they are connected by rather simple diagonal similarity transformation.
What is the counterpart of the quantum parameter?
Quantum parameter?
The Q parameter.
Okay. So for XXC, of course, there's a delta.
Yes,
so delta is maybe P over Q times Q over P, something like that.
P over Q. I see. So in the, I see. So TSF case, it's a classical.
Well, it goes to a different limit.
Some other parameter.
Right. Yeah. XXC.
I just missed what the answer. So the limit to XXX corresponds to what in this?
XXX corresponds to SEP, symmetric case.
That's SEP. Okay, thank you.
So this is finite size system?
This is a little bit a tricky point. So this exact connection is valid for the case with no particle input and output in the language of ASIP. This corresponds to UQSL2 symmetric XXC. So this connection is exact. But for example, the periodic ASIP and the periodic XXC are not really connected, right? But so a little question is, what about the infinite case, right? And we are in particular interested in infinite case. They are kind of equivalent, but we have to be a bit careful. Okay. Anyway, is it okay now? Any other questions? Okay. Okay. So so this ASIP is a kind of particle hopping model, right? Particle transport problem in non-equilibrium statistical mechanics. But so there's a simple mapping from this particle hopping model to surface growth model by replacing empty side by upward slope and occupied side by downward slope. So then this particle configuration of ASIP corresponds to surface configuration like this, and the particle hopping to the right here corresponds to local height growth in the upward direction of the same place, right? And the fact that there is a net current to the right, maybe for A shape, corresponds to the fact that this surface grows in upward direction in average, right? And the current corresponds to the height, and we are interested in fluctuation of current, which corresponds to fluctuation of height in this surface growth picture, right? They are kind of equivalent, and for this surface growth model, so there is a kind of another standard model called Carter-Paris-San equation, and this shows quite a large universal behavior, which is often called KPZ universality, and A-shape is also in this class. And by studying this model, we can study also universal behavior of this KPZ. And yeah, so the studies of this type of models has been progressing for the last 10 or 20 years, very, very extensively and intensively. And this is now almost forming a kind of a little field in the kind of intermediate region between probability theory and the non-equilibrium statistical mechanics, and this is called integrable probability. Of course, you may think that this is just a quantum integrability, but somehow, so these models have particular nice property that, for example, summations of excited states can be performed so that we can get precise information of distribution and correlation functions. So this kind of aspects gives further motivations to study these kind of models. And so at this point, this is quite a mathematical, just a model problem. But in fact, there's also a nice experiment using liquid crystal about this universal behavior of KPZ, right? And so there's a 1/3 non-trivial exponent, and one can also measure the distribution function. And this matches well to this theoretical prediction. And this is also related to random matrix theory. But this is different from my main subject today. So this is just a kind of general introduction to our interest in non-equilibrium statistical mechanics and some connections to integrable systems. Okay, so but today, as I mentioned already, I stick to the symmetric exclusion process. And in particular, we focused on so-called large deviation properties of the current for this set. And so this kind of problem is a kind of classical problem for us. And so there is a kind of one general theory which was kind of initiated and developed by Yonaracino and the group from around 2000. This is called Microscopic Fluctuation theory. And we may abbreviate this as MFT. And so this gives some prescription to describe the large deviation property of this classical, in particular, diffusive systems. And in fact, but in probability theory, basically, the kind of almost equivalent formulation was already established by Kipnis more than something like 10 years ago. But anyway, so the net result of this MFT for the case of set is that so the large deviation is described basically by using intermediate solutions to the so-called MFT equations. And the MFT equations for set are coupled nonlinear PDEs. So this has been considered to be difficult, right? And in the meanwhile, so there are some microscopic calculations using beta anders because as I mentioned, SEP is also integrable, basically Heisenberg spin chain. So already in 2009, Days and Gershenfeld could study the large deviation for the current at the origin, and we also succeeded in generalizing this result to any position current large deviation and target particle problem. But so this was not solving this MFT equation. But today I want to report on our recent result that now we have found a kind of way to solve these MFT equations by mapping these MFT equations to classical integrable systems, right? And in our case, it has turned out to be the so-called rather generic case of AKN system. And to achieve that, we found a non-local generalization of the canonical core Hopf transformation. Okay, yeah, but yes, I have to mention that for stationary situation where T derivative goes away, So there had been some exact solutions already for MFT equations, but for t-dependence case, this has been considered to be difficult, and this is what we could achieve recently. Okay, but for people here, maybe some of you don't know really about the kind of fluctuations and large deviations. Let me start from very basic stuff. So let's consider a case of simple random walk, right? I believe that you know random walk. Yeah. So let xi to be ii this independent and identically distributed Bernoulli random variables, which takes value 1 with probability 1/2, takes values -1 with probability 1/2. And we take a sum up to n, xi n, and this is called xn. So this can be considered the position of random walker, right? At time n. And of course, these are independent, so it is easy to calculate average, which is 0, and the variance to be basically proportional to n, as you know. And of course, this is squared, so basically this means that the typical fluctuation is on the scale of a square root of n, and on this scale, we see Gaussian distribution. So this is a central limit theorem, which you know very, very well. But in large deviation theory, we study more atypical event in which we look at the probability that this position scales like n, right? Of course, a typical fluctuation is living on the square root of n, so this probability should go to 0. But we are interested in how this probability tends to 0 as a function of maybe n. So then we can, for this case, we can expect that so this probability decreases like e to the power minus some function of y times n, right? And we're interested in this function phi of y. So for this particular case of simple random walker, so this is simply given by this binary entropy function, and this phi of y is called rate function. And for this particular case, this has this kind of shape. Right? Is this clear? And of course, we are interested in calculating large deviation function for interacting particle system, SEP in our case. Okay. Okay, so let's recall the model again. So we consider one-dimensional SEP symmetric case. So now particles of in a symmetric manner. And maybe we can also introduce occupation variable eta x of t, which is 0 when the site x is empty at time t, and 1 when site x is occupied at time t. And as I already mentioned a little bit, we are interested in the current for this model. And in particular, we are interested in integrated current at the bond between this site 0 and 1 between time 0 and t. Right? And we can also consider the target particle problem, which starts from the origin. But today, we are mainly interested in this integrated current. And there is also a nice limiting case of this set in which we take the Brownian motions limit of these random walkers. So yeah, so the trajectory may look like this. This is x-axis, this is t-axis. So some particles, Brownian particles, start from various positions randomly, and they do symmetric random walks. And so when they collide, they do symmetric reflection, right? And so then, yeah, so this is called, sometimes called Harris systems, or we are calling this a Brownian, reflective Brownian motions. And we can also define the corresponding quantity, integrated current, target particle position for this system as well. But so kind of simplification aspect of this limiting case is that when we look at these trajectories, so this is equivalent to the trajectories of independent Brownian walkers. I say that the particles do symmetrical reflection, but when we are only focusing on the trajectory, this is equivalent to just an independent Brownian motion with which in which the particles are just crossing, right? There's no reflection. So, and for these quantities, we can just consider properties of this, which seems rather trivial, right? And in these cases has been solved a long time ago because this is basically free case. But today we want to study the symmetric exclusion case. Okay, and of course, we have to specify initial conditions to really study some fluctuations. And then basically, our scheme will work for general initial condition. But for the moment, let's stick to some simple initial condition in which we take sort of step initial conditions with two densities. So at time t equals 0, the left sides are occupied independently with density rho minus, and the right sides are occupied with density rho plus independently, right? So then, of course, stationary case is one of the most important case, and this can be realized simply by setting rho plus equal rho minus equal rho. Okay, I think the model and the quantities are defined and clear. And before going to large deviation, maybe we can recall the known results about the typical fluctuations. So this is a kind of replacement of central limit theorem for random local, right? So yeah, already there's some non-trivial aspect for symmetric exclusion process coming from this exclusion interactions. The typical scale is living on t to the, so large t is a kind of large time which we measure the current and so on. Capital T to the power 1/4, not 1/2. But anyway, so this can be shown, and this was shown for the case of target particle long time ago by some probabilities. So now we are considering that for the case of uniform density, the average is of course 0, and variance can be calculated to behave like square root of t. So this gives us this t to the 1/4 typical fluctuation. And this can be basically translated to the average and variance for this integrated current, and these are the results. And this 1/4 experiment has been attracting some attention, and this has been already confirmed in some experiments. Okay, but today we want to focus on the large deviation for our quantity Qt, and because of the typical fluctuation scaling into the 1/4, the large deviation is suitable to be considered at the scale of square root of t. So let's consider this probability. So then we can expect that this again goes to 0 when capital T goes to infinity, and in such a way that this is like a e to the power minus square root of t some function depending on q. Basically, we can think that we want to calculate this phi for the case of symmetric exclusion process. Right? And so this is probability, but by Legendre transform, this problem is equivalent to the calculation of generating function for the current. So we can focus on the calculation of this average of e to the power lambda qt, which is expected to behave like e to the power square root of t times mu of lambda. And we're interested in this mu of lambda. And once this is calculated, then this phi, large deviation function, or rate function itself, can be just obtained by doing Legendre transform. Right? And yeah, I'm saying that maybe we can think that our primary goal is to calculate phi, but of course we are interested in other quantities and behaviors of the system, for example. So we are considering kind of rare event, right? And to realize such a rare event, the system should organize itself in a particular way. And for example, the density profile should be different from the usual hydrodynamical behavior. And we are interested in what kind of density profile the system shows when this kind of rare event is realized, right? So these kind of issues we are interested in. So let me mention a little bit about the microscopic fluctuation. So this is a whole theory, so I cannot really explain the whole details, but let me briefly explain what it is. So we are considering microscopic model called SEP, symmetric exclusion process. But when we are interested in large deviations, it is expected that this can be determined simply by the quantities called diffusivity and for the mobility, which is calculated to be this function for the case of SEP. And so it is also expected that the large deviation properties is shared by the Langevin equation in this form. So now density rho is a fluctuating density field, and the time derivative, this is diffusion, and so this psi is Gaussian white noise in depending on x and t. And if we put square root of mobility, which is compatible with this fluctuation dissipation theorem, so then so this can be kind of considered as also as a microscopic model which has some fluctuation, right? Yeah, so it is we can expect that this Langevin equation and the set share the same large deviation property. If we take this sigma to be this one, then we want to study this thing, and so we want to study this quantity, which was just this one, right? For this Langevin equation, then we can use sometimes called Msr formulation, which gives functional integration, path integral expression for various quantities for this type Langevin type equations. So then, as a result, we can write down some functional integral formula for this quantity in this way. So now the rho is coming from this density field. We do functional integration over rho, and we have to introduce another auxiliary field coming from this noise. And this we call H, capital H here. So then we do functional integration over two fields, rho and H, with some kind of action, which we call MFT action in this case, which is given by this formula here. And this lambda qt is just coming from lambda t. And so this f naught is written in this way. This may look a bit complicated, but this is coming from initial condition contribution, which we took to be Bernoulli random initial condition, right? Which is very, very simple. So yeah, from the appearance, so this is rather simple term. So we are not put so much emphasis on this, but most non-trivial part is contained in this integral, and this is given this way. So this is basically the usual action in the form of usual action, right? And this curly H is given this way for this problem, and this is sometimes called MFT Hamiltonian in this case, because this can be considered as a Hamiltonian system. Anyway, so this is a kind of formulation of large deviation in this scheme of microscopic fluctuation theory. Now, yeah, so sorry. At this point, so this is just this is not about large deviation. This is for all fluctuations. Now, if we want to focus on the large deviation, then we take capital T to large. So then we may expect that the contribution for this whole functional integral is dominated by rho and H, which maximizes this MFT action, right? So then we can just do the usual variational calculation, writing down with a Lagrange equation for this Hamiltonian. So then the optimizing path of rho and H should satisfy these two equations. So this is the MFT equation, right, for our set. And so these are, yeah, for rho, so this is diffusion, and there's some contribution from H. For H, so this is anti-diffusion, and there's some nonlinear term. Anyway, so these are coupled, this is coupled nonlinear PDEs. And once we can, sorry, and before that, we also have to consider the boundary conditions at time 0 and t. And so the condition at the final time is easy. And this is just given by lambda times Heaviside step function. Initial condition is a bit more complicated. There's some contribution from initial condition from here, but this can be written down where f prime is simply this function. And anyway, so if we can solve these coupled nonlinear PDEs, MFT equations with these two boundary conditions at initial time and the final time, and if we can put them into this MFT action, so then that will give us a late function for set, basically, right?
Sorry,
Yeah.
I have a question. So the question you wrote down looks similar to KPZ. Is that a coincidence or is there a reason?
Which one? This one or
No, the one for H, the second equation, for example.
this one?
Yes. Is it just a coincidence, or are you talking about something completely different, or are you these two related?
Basically, I would say this is a coincidence.
Oh,
But
coincidence.
there could be a little bit more deeper reason, but which we don't quite understand.
I see. Thank you.
Thank you. Okay, but so we want to solve these equations for the case with sigma given by rho times 1 minus rho. But before going that, maybe I would mention that for the case of reflected linear motion, for which sigma of rho is simply given by 2 rho, so these equations become much simpler. So if you put this into here, yeah, so these are still coupled nonlinear PDEs, but there's a nice transformation even here. Which is called canonical Kohl-Hopf transformation, because e to the power h, this is called Kohl-Hopf transformation. And we also introduce kind of corresponding transformation for the other variable q. So this is often called canonical Kohl-Hopf transformation. And then if we apply this canonical Kohl-Hopf transformation to this MFT equation for the case of RABM with this sigma, then these are just linearized. So the first one becomes a simple diffusion equation. The second one becomes anti-diffusion with a negative sign. But anyway, so these are separated linear equation so that this can be solved rather easily. And this, yeah. Yeah.
I'm understanding something. So this is basically, yeah, Kohl-Hopf is a sort of generalization of the Riccati transformation for going from the Riccati equation to the Schrödinger equation. Am I right? So this is what you do.
Yeah.
Because the Riccati equation is non-linear, you take the exponential, the wave function as exponential, you go to the Schrödinger equation.
Right.
You have two variables here instead.
That's right. Yeah.
Two independent variables, which are H, rho.
Yeah.
Is it so? And it depends a little bit on the fact that the right-hand side of the second one has the so-called Mura form, no? It's the derivative square plus the second derivative, which is the same as in the Riccati equation.
That's right. Yeah. Thank you. Okay, but today I want to show how the equation, this MFT equation can be solved also for the case of set. Right? Yeah. So this is almost identical to the previous one, but yeah, this part is only different. Okay, but in fact, the solution is quite rather simple once you know the solution. So yeah, we found a kind of generalization of this canonical Kohl-Hopf transformation in this way. So we define two new variables, small u and small v, in terms of the variables rho and h, which appeared in MFT equations, right? Yeah. So then, in terms of these new variables, small u and v, the MFT equations for set, this one just become these equations, which is again a couple of nonlinear PDEs. So there seems to be no progress, but of course not. Indeed, as some of you may notice immediately, so this is one of the well-known classical integral systems known as AKN system, Pavlovitz-Neville-Seeger system. So yeah, now these are coupled nonlinear PDEs, but now they are classical integral. So by using basically a standard scheme of classical integral system, one should be able to study MFT equations, and then one should be able to calculate large deviation for symmetric exclusion process. That's the basic idea, right? And one small little remark here is that when we take rho goes to zero limit, in which we may expect that set tends to the reflected linear motion, then this becomes canonical Kohl-Hopf transformation. Basically, yeah. So this goes away. So then you can integrate this to get minus h on this h in this way. Yeah. Anyway, so we found this generalization which works for set case. And of course, we also have to transform the initial and the final condition for MFT equations in this language of phi and v. And so now this has turned out to be quite simple indeed. So we are considering not completely trivial initial condition, right? Two density initial condition with two parameters, rho minus and rho plus. But in the language of this new variable, small u and small v, so both conditions become simple delta function condition. Omega should be determined in terms of u, v, rho plus, rho minus, and lambda. But anyways, they are proportional to delta, which is much simpler than the original problem. And to have a full solution in the original language, we also have to write down some transformation between uv and rho h more concretely with new parameters or constant, capital K and capital lambda. But yeah, probably today I don't have enough time to explain the details. But okay, but today I am telling you that we have done everything. It may have some like that, but there are some previous works like this. Yeah, first of all, we thought that yeah, okay. So I have to be a bit short. So yeah, so there are some previous works which seems to a little bit noticing a possible relation between this kind, not completely the MFT equations, MFT-like equations and the classical integrability around 2016. So that's one reason why we started to work on this. But for a while, there are nothing except these our microscopic calculation. But last year, so there appeared a few very much related works on different problems. But yeah, we also took some inspiration from these recent results, and then we could solve this case of set. So there's, yeah, so it's a bit difficult, a bit tricky how to describe the situation. But there was a talk by Racino in this May, and he described in this way. So this kind of agrees with our way of looking at things. So let me just quote it. So this is something I mentioned already. So far, it has been confirmed for the stationary state. So not t-independent case, but the time evolution is more difficult. This is what has been done, right, recently. And so there are some previous works on weak noise KPZ by Krajenbrink with the south. Okay, another model called KMP model, Bettelheim-Smith. So, but in these cases, the MFT-like equations are already kind of classical integrals. But we had to, in the case of set, we had to find this nonlinear transformation, right? So this is a big difference. But anyway, okay. And so from now on, I will basically skip this. What we do is just basically apply the usual scheme of classical integrability. So this kind of scheme should be familiar to you. And so there are some new aspects that we have to, instead of, so usually for classical integral system, we use inverse scattering method. We start from initial condition, go to scattering amplitude, do the trivial time evolution, and go to the final time function, right? But in our case, slightly different aspect is that so we have two conditions at initial time and final time. So instead of going this way, maybe we can do partially apply the direct scattering here and here both, and then compare this. But anyways, the idea is quite similar. And in the end, the problem is reduced to a scalar Riemann-Hilbert problem, which can be rather easily solved by using Cauchy transform. And then we can also determine these constants, omega, lambda, cap, k. And then, yeah, so these are. So then we can go to the final results for density profile and the cumulative generative function or large division function. And for density profiles, rho, we could find this kind of explicit formula. And similarly, for initial time, we could also write down some formula. And so now we could draw some figures for this density profiles, which realizes some rare events, which realizes some, yeah, atypical current fluctuation. So this kind of thing had not been possible, right, before our solution. And we could also study the cumulative generative function explicitly by putting the solutions of the MFT equation into the MFT action. And so for the particular case of these two densities, we found that this agrees with the derivation field result, microscopic calculation. So now we are thinking that this is a kind of first analytical confirmation of the prediction of MFT for interactive model in time-dependent regime. So there was some kind of physical assumption to describe large division by MFT equations, right? But our solution for MFT equations agreed with this microscopic equation. So this is a confirmation of the MFT. Okay, so then to summarize, yeah, we have presented the first exact with MFT for SEP. And we could find the mapping from MFT equations for SEP to classical integral system, AKNS system. Yeah, so the key of our result is this generalization of the canonical Hopf transformation. So for the moment, we are sticking to this step density with a step initial condition with two densities. And yeah, this is a confirmation. And yeah, as you see, so the scheme is quite general. So there should be various generalizations. We have been really working on this, but yeah, for the moment, they have not been able to. I have not been able to finish this by today. So I was hoping to show a little more, but yeah, maybe for next time. And so the main subject today is a connection between large deviation MFT scheme to the classical integral system. But as I also mentioned at the beginning, there is a quantum or stochastic integrability for ASAP and these kind of models. So there should be some relation. And I would like to kind of try to clarify this during the stage. Yeah, thank you very much for your attention.
So, of course, here you have a Lux formulation you sketched, and also AKNS allow for soliton solution, which are maybe not your initial solution, but do the soliton have any meaning in this phenomena?
For our case, it does not play so important role somehow.
Say again, please.
Solitons, right?
Solitons, yes.
Solitons,
well, if you have some for some particular initial condition, you will get soliton.
Yeah.
Many solitons, sorry, and soliton solution, which is so is somehow the modern appearance of soliton in Fermi-Ulam pasta model, right. No?
Of course, in old works, people try to find particular initial condition in which only solitons appear, right? But in our case, we want to solve particular problem for given initial conditions. In that sense, we cannot stick to the case with only solitons. But already for our problems, so soliton have some kind of soliton appears, but it does not really play important role for example, this kind of function.
Yeah, soliton should have some characterization. For instance, are characterized by reflectionless potentials. So a special how do you call the scattering amplitude you call, no? So the zero reflection coefficient, something like this.
Right.
So a bit actually related, similar kind of questions to the last one. Do you expect to get classical integrable systems out of this construction from the beginning, or is that a surprise that they are? These differential equations you end up with, do you expect them to be classically integrable, or
yeah,
a priori from the beginning?
So maybe I don't get the question precisely. So these equations is well known to be classical integrable.
Right, so but you derive them, right? You derive. I mean,
derived from the MFT equation.
Do you expect the MFT?
This is a well-known equation which is integrable, right?
Right, yeah, but I guess my question is, starting from the models that you start with, do you expect these MFT equations to be classically integrable, or is that something?
This I don't know yet.
And for example,
I mentioned a little bit. So already the microscopic model, symmetric exclusion process, the generator is basically the equivalent to Heisenberg spin chain. So this is quantum integrable. So even after taking some limiting thing, we may expect that
okay.
yeah, something integrable should appear, but this has not been really noticed clearly until our work.
And I guess related, do you have some kind of idea if you perturb away from this symmetric point, how this story is modified?
That would be some interesting question. Another little bit interesting situation happens for the case of another model, KNP model. In that case, KNP model is not integrable as a microscopic model, but when you consider this large division, MFT equations is integrable system. And but after that, then a group of people found that there's an integrable version of microscopic model, which also goes to the same MFT equation. So yeah, already at the microscopic level, one can expect some possible appearance of classical integrable system, but it's not so clear. Yeah. Mm-hmm.
And then maybe just one wild question. So I'm not so familiar with this topic, but just I guess the story I know where there is a relation between quantum and classical integral systems is this ODIM correspondence. I don't know whether is that something completely. If there is any.
I don't know so much about this correspondence, but for the moment I don't see any
connection at all. Okay, thanks.
I have two questions. The first one is this MFT equations. You just look for the saddle point of the action, right? Yeah. Is there any correction to this? Yes. Is there any correction?
Correction.
You can calculate.
Yes, there should be corrections.
Yes, but is there any known result for this?
Sorry, I'm not sure.
Okay.
Are you thinking about possible still?
Yeah, something like instanton corrections.
Yeah. I don't know. Yeah, that may be interesting. Thank you.
The second point is, at some point you mentioned that this random formulation is somehow used for computing or summing over the excited states.
Excited states.
Like computing correlation function, then you have to sum over excited states to get. And
yeah.
And
this was about microscopic model, I guess.
Yes, microscopic model. Can you explain a little bit about this? Is any what kind of?
Okay, this is a bit different from the main subject. Yeah. So our basic formulation of this classical model was a master equation, right? So then maybe we are interested in some average. So then basically we want to, so this may be considered some matrix element with some particular state. So we can write something like this. So this is different from the usual quantum case, right? Because in the quantum case, so we sandwich with the same state. But so this is classical probability, so we just use a kind of linear one, just one single one. But anyway, you can insert this complete set. So then you can try to calculate. And even for XXZ model, as far as I understand, this summation is usually difficult to take. But magically, for the case of ACID, this can be done for some particular case. So I think this is what I meant. Yeah.
Thanks.
Yeah, sorry, maybe it's a little bit over time, but I'm still tempted to ask. So one context where KPZ appears, sorry, it's a little bit outside your main talk, but one context where KPZ universality class appears is the evolution of the entanglement entropy. under the random dynamics. It's actually related to the talk by last week.
That's
and then
right,
it grows. But then in that context, you can also include a measurement, as in the last week's talk, to start decreasing. And then there's a computation and phase transition. So do you know if there's a way to incorporate the effect of the measurement? So it should be some parameter deformation of the KPZ to incorporate that. And there should also be a nice connection there, I feel.
I see.
Do you know if there's a candidate?
Thank you. I haven't thought about such, but it may be possible, in different contexts.
At least in that context, it's very quantum, right? So it's a very quantum regime, whereas what you're saying is classical. So it's a little bit non-trivial, I feel.
I haven't thought about it, so thank you.
Yes, thank you.
If there is no other question, I will ask a question. So often we have a relationship between quantum and classical integrability via particular solutions of quantum integrable systems, and then you can retrieve a classical solution, a classical limit of the solution. So is there any relation like this in the case of SEP? Can you imagine that you have some particular solution of x66 that you are looking at, and then you are taking a classical limit of the solution, and then you will get to this these classical equations?
Maybe it's just it. That may be the case. I was mentioning that there's a relation between this generator for ASEP and Hamiltonian weight 60. So there's some transformation. And as I also mentioned, even though they are very simply connected, the physical interpretation is quite different, and the condition which should be satisfied these matrices are also different, right? So this should satisfy classic stochastic condition. This should satisfy Hermitian condition, and so this transformation kind of changes these conditions. And MFT equations are written basically in this language, and this was considered to be difficult to solve because this is coupled nonlinear PDEs. But in fact, maybe we can try to formulate the large deviation in this language, and this may be already pretty close to what we have been doing. That may be the case indeed. So, and if this is the case, we have a kind of better kind of point of view to study at least a large deviation of the classical systems. So this may open up some nice new approach to study this kind of questions for classical problems, I think. Thank you.
Thank you very much. If there is no other question, let's thank Tomohiro again.
Thank you very much.